show two example applications of the Poisson approximation technique. The first one is about maximum load. So here we are going to throw n balls into n bins. So the number of balls is the same as the number of bins. And then we let L to denote the maximum load. Previously, we have shown that with high probability, the maximum load is less than or equal to 3 log n over log n. And here we are going to show that for high probability, this L is going to be greater than or equal to log n over log n. So precisely here, we are going to show that this maximum load less than log n over log n is going to be a small probability. So how do we do? So let's see. So here, let us say we use big M to represent a parameter to be fixed later. Actually, this M will be set to log n over log n later. And to get the result, we are going to use Poisson approximation. So we are going to assume that we have n random variables. Each of them is an independent Poisson random variable with parameter 1, because the expected number of balls in each bin is equal to 1. So in this Poisson case, the probability that the first bin receives n plus balls will be greater than or equal to the probability that the first bin receives exactly n balls. And since this is a Poisson random variable, the chance that bin 1 receives exactly n balls is the same as e to the power minus 1, the parameter 1 to the power m, divided by m factorial. So this, after simplification, this is 1 over bracket of em factorial. And again, in the Poisson case, so here we can analyze the probability that the maximum load is less than n. Now notice that in the Poisson case, all the bins are independent of each other. So this probability is easy to compute. So this will be less than or equal to the chance that every bin has less than or equal to n balls. So, or less than n balls. So this is the probability that it has more than or equal to n balls. So 1 minus this one is less than n balls. And then we need all the bins to follow this restriction. So we have this probability to the power n. So this one, when m or n is very large, then this one is roughly e to the power minus 1 over e to the em factorial. So after collecting terms, then this is e to the power minus n divided by em factorial. Now this is the Poisson case. And because we are talking about the maximum load, we can use the results of the special case. So in that case, the probability of the maximum load in the exact case will be less than or equal to 2 times the probability of the maximum load less than m in the Poisson case. Yeah, indicator. So this is a non-negative random variable. This is the expected value of a non-negative random variable, and this is the expected value of a non-negative random variable. So all that remains is to find a proper m so that the right-hand side is small. So what we want here is this is the right-hand side to be smaller than or equal to 2 over n. Okay, if we want to have something like this, then it is the same as by taking, so we can take log on both sides, move terms around. So the corresponding m that we should find should satisfy em factorial less than or equal to n over log of n. So in other words, we want em factorial to be less than or equal to this one. So we can take log on both sides so that we want log of n factorial to be less than or equal to log of this one, which is log n minus log n. And there is a e here, so there is minus 1 here. So this minus 1 minus log n is not very important because this is the most important term. So So if we set big M to be log n over log n, then we will see that the left-hand side bound is log n factorial, right? So for the left-hand side bound, log n factorial, we plug in this one so that we will get log of e square root m over e to the power m. So this is the approximation that we have m factorial is less than or equal to this e square root m over e to the power m. We have shown this before. And then when we take log, then the most important term is actually m log of m over e. So we have m log of m minus m. So this is m log of m over e. And then these are the non-dominating terms. And then by setting things like this, then the first term is log n over log n multiplied by log of log n over log n. So roughly, this is like log of n. So less than or equal to log of n. And then for this other term, previously, this is like minus of a big term log n over log n. But then here we are minusing some smaller term, log n instead. So we are also making the overall things larger. So in that case, after doing this plug-in of log n over log n, we will see that this term is indeed smaller than or equal to log n minus 1 as we want. This is what we want. So because of this, we are done. So we have now shown what? By setting m to be like this. So this m is like this. So the probability of the maximum load less than this one is going to be super small. So in most of the cases, the maximum load has to be greater than log n over log n. So this is our first example. Okay, let us look at our second example. This time, we want to revisit the coupon collectors problem. So let us recall a little bit about this problem. So we have a set of we have n different types of coupons, and then each time we can draw. For each time we draw, we can get one random coupon. Our target is to get a full set of n coupons that contains each type of this coupon. And previously, we have shown that the expected number of coupons to buy is n times the harmonic number of n, and this value is roughly n times log of n. Now today we ask a different related question. This time is we are setting that we are not considering of getting the full set. This is our target. Instead, we have constraint that we can only buy n log n plus cn coupons. So we have only money for buying this number of coupons. But then we want to ask, what is the chance that buying these many number of coupons, we could get a full set? So here, let us have some very quick analysis. So let T to be the number of coupons that we are going to buy. So T is equal to n log n plus Cn. So after buying T coupons, the chance that we do not have a particular coupon is 1 minus 1 over n to the power T, because each time we do not get this coupon. And this value is roughly e to the power minus T over n. And T over n is log n plus c. So this is the same as e to the power minus c coming from this c divided by n coming from the log n. So e minus c divided by n. So this is the chance of not getting a particular coupon. So the chance of not getting some of the coupon, at least one of the coupon, is less than or equal to this term multiplied by n. This is by union bound. So in that case, the chance of getting a full collection, we can analyze that this is going to be greater than or equal to 1 minus e to the power minus c. Okay, so this is a very simple bound that we obtain without using any other new techniques. We just use the union bound. But today we have learned Poisson approximation. So let us get a better bound. Moreover, we have also learned about the Chernoff bounds for Poisson random variables. So in that case, let us combine what we have studied so far and hope that we can get a tighter answer for the previous question. So here, this is the theorem that we will obtain. Suppose that X denotes the number of coupons to buy before we get a full collection. So X is the eventual number of cards until we get a full collection. We are claiming that for any small enough C, the chance that X is greater than n log n plus Cn when n tends to infinity is equal to this strange term, 1 minus e to the power minus e to the power e to the power minus c, so this strange term. So here we assume that c is going to be a small value independent of n, and then n is going to be a very large value where it tends to infinity. So we show that such a limit exists and it is equal to this value. Now let's plug in some term for this c to understand more about what this means. So when c is equal to minus 4, the right-hand side term here is roughly equal to 1. Reason is that c is equal to minus 4. So minus c is equal to 4. So this is minus e to the power 4. So it's like minus 3 to the power 4 is like minus 81. So e to the power minus 81 is going to be super small, close to 0. So 1 minus 0 is equal to 1. So we get something like close to 1. On the other hand, when c is 4, then this is e to the power minus 4. So the top part is like 1 over 81, something like this. So e to the power minus 1 over 81, so it is close to e to the power minus 0. So it is close to 1. So 1 minus 1, it is close to 0. So in that case, when c is equal to 4, the right-hand side will be a value very close to 0. So what does that mean? It means that X will be like bounded by n log n minus 4n and n log n plus 4n with high probability. For most of the probability, it is concentrated for X within n log n plus or minus 4n. So what does that mean? It means that in most of the cases, the total number of coupons that we actually need is close to the mean value, n times h of n, plus or minus 4n. Okay, now let us focus on how to show this result. Okay, so first of all, naturally, the coupon collector's problem can be considered as a balls and bins scenario. So we are going to create n bins, each bin for a particular type of coupon, and then we are going to throw balls. So we are going to throw n log n plus cn balls, so that each one corresponds to a draw of a random coupon. And then we want to use this balls and bins scenario to represent the coupon collector's problem. And to obtain the previous theorem that in the previous page, we are going to apply Poisson approximation. So the number of balls in each bin this time will be a Poisson random variable with the average number of balls in each bin, which is log n plus c. And the expected total number of balls is equal to, so we call it m here, and it is equal to n log n plus cn. So in the Poisson case, this is what we have seen as before, but let's do this again. So the chance that bin 1 is empty, so this is a Poisson random variable with parameter m over n, so that the chance for this random variable is equal to 0 is e to the power minus log n plus c, and after simplifying, this is e to the power minus c divided by n. So the chance that we do not have, so we do not have any empty bins means that bin 1 is not empty, bin 2 is not empty, and so on and so forth. So this is exactly the same as 1 minus the chance for a certain bin is empty to the power n. And this is equal to e to the power minus e to the power minus c when n is large. Now, to simplify our notation, we use NE to denote the event that there is no empty bin. Okay, so NE means no empty bins. Okay, now let us further define some new random variables. We let y to be the total number of balls thrown in the Poisson case. So y could range from 0, 1, 2, 3 up to infinity. And then y is the Poisson random variable with parameter m, the total number of balls in the exact case. We will let r to be a parameter to be fixed later. So roughly speaking, r is of the order of the square root of m, okay? So it is going to be a small value with respect to the number of balls that we are going to throw. Now, based on the value of r that we will set later, we will have the two bounds as follows. The first one is the probability that y minus m greater than r is equal to 0 as n tends to infinity. So here, this is like, all these are about limiting terms. So as n tends to infinity, the chance that y is away from the mean value of y, this is also the mean value of y, right? Greater than r is going to be super small, equal to 0 as n tends to infinity. And the second one is interesting. So the probability of having no empty bins, given that the condition that y is close to the mean value, will be the same as the probability of having no empty bins, given that y is exactly the same as the mean value. So normally, it is difficult to compare conditional probability. But thanks to the relationship of the Poisson case and the exact case, then we can later somehow compare these two terms. Okay, for now, let us assume that we will have an R such that these two bounds will hold simultaneously. Then the consequence is this one. The probability of having no empty bins in the Poisson case. So here we are talking about Poisson case all the time. We have just shown that this is equal to this term. By using the conditional expectation formula, we will see that this probability can be expressed as the conditional probability weighted by the corresponding probability. So we have probability of this condition and the probability of the opposite condition. And then we calculate each of these probability, and then each of them is weighted by the corresponding probability to occur. So in that case, we will have probability of no empty bins is equal to the sum of these two things. But now we are assuming that the two bounds are correct. So this comes from the first bound. There is no chance for y greater than r from the mean value. So in that case, this is going to be 0, so we don't care about this probability. And then for this one, if this is 0, then this is 1. So after simplification, we get this is probability of NE given y minus m is less than or equal to r. So this is what we can get so far. But then based on the second bound, this probability is the same as this probability, right? So this is the second bound. And this is the conditioned Poisson case. So conditioned Poisson case is equal to exact case. So this probability is the same as the probability of no empty bins in the exact case when exactly m balls are thrown. So we are nearly done. Okay, so the chance of having no empty bins in the exact case is this value. So that means that the chance of having some bin non-empty, so that was no empty bins. So the chance of having some bin to be empty, okay, the opposite will be 1 minus the strange term e to the power minus e to the power minus c. But if I tell you that some bin is empty, it means that the total number of coupons that we need to draw must be greater than the total number of coupons that we have now just drawn. Okay? So when some bin is empty, the total number of coupons that we need to draw eventually to get a full collection must be greater than m. So this implies x greater than m. On the other hand, x greater than m implies that at the time when m balls are thrown, some bin has to be empty. So these two statements, these two conditions, some bin is empty when m balls are thrown, and x greater than m, they are equivalent to each other. And this is exactly what we want to get, okay, in the first page, okay, in our theorem, okay. The m value is this one. So the probability of x greater than m is equal to this one. So we have now just shown that. So let me get back to this one to be equal to this one. Is that okay? So we are now done, except that we have to show the two bounds based on this R to be correct. So we will leave this in as the third part of this lecture.